Hello everyone, welcome back to another video for the series. I'm you, and today I brought a very fun and interesting geometry problem. This problem taught me lots of basic things. So, you know, as many of you know, I didn't prepare for like JMOs, or I didn't prepare for middle school KMO. So I don't know like those basic stuffs, but this problem helped me to learn them and somewhat review other elementary stuffs. So that's why I thought this problem was really valuable for me and decided to share it with everyone. So yes, uh, let's start. Let ABC be a triangle and let omega, is it the omega, be its incircle. Denote by D sub 1 and E sub 1 the points where omega is tangent to sides BC and AC respectively. Okay, so we have, I can't draw. Okay, so we have a triangle like this, and we have in center omega, uh, something like this. Um, Starting to see the shape. Uh, I don't know why, but it's so hard to draw circles here. Yes, so let's call this omega in here A, B, C. But I want our circle to be quite thin because we need to label some of them. Oops. Oh, cool, this is great. Okay, so this is omega, and denote by D sub 2 and E sub, so this point right here is D sub 2, and this point right here is E sub 2. The points on side BC and AC, what? Oh, D sub 1, sorry, D sub 1. Points denoted by D sub 2 and E sub 2, the points on side BC and AC respectively, such that CD sub 2 equals BD sub 1. I guess B sub, so this one and maybe D sub 2 should be here somewhere. I think so. And C maybe here. A D sub 2 and B E sub 2. And this intersection right here, we denote it as P. Circle omega intersects AD sub 2 at 2 points, the closer of which to the vertex A is denoted, so this one is Q. Prove that AQ equals D sub 2 times, so this length and this length are the same. Let's make our drawing bigger to make it better. Oh, I didn't know that it was this bad. Okay, so we have our omega right here. and this length and this length are the same. Yes, I'm starting to like my figure. Yes, not bad. Okay. We just need to prove that the red ones, or I will just highlight it. We want to prove that this length and this length are the same. AQ and P, yes. And I'm going to denote it with different colors. So, oh no. So this one, this length, and this length are the same. And B sub 2, wait, C D sub 2, so, and they are the same, so this length right here and B D sub 1. And they are the same. Yes. So I think there is one thing that we all should think of when we see this figure, and that is X center. So we're going to draw an X center with respect to A. So the way we can do that is by extending it like this. Extend this line. And draw an X circle. This will be a tough job, but let's try. No, that's not good. Okay. I'm starting to see the shape, I think. No? Never mind. I don't think this is a good one. Maybe if I erase some of those lines, I may see it. I mean, we don't need like the entire X circle, so I'll say good enough. Yeah, it's good enough. Yeah, I think they're good. Yay, we got our X circle. Now we know that. Oh no, I need to erase this one. Yes. We know that our X circle right here touches, or is actually, I think my marker here is too thick. Let me just use different colors. Oh, yes. So, these ones. So what we see right here. So this length and they're the same. They're given by the problem. Yes. Oh, sorry. Yes. Now what we're going to do here is we know that our X circle actually touches, or is actually tangent to BC at D sub 2. So let's call these omega prime. So we know that omega prime is tangent to BC at D sub 2. And I will actually prove this in my next video. So yes, I will try to prove this in my next video, so please look out for that. And we also know that omega and omega prime are homothetic with respect to A. And I'm also going to prove this later. I mean, not later, in my next video. So also, please look out for that. And what I mean by that here is AQ. AQ to Q D sub 2 is equal to AE sub 1 to, let's call this A to here. So read A, B, C, D, E. We don't have F and G. So let's say that this is F and this is G. We know that. Therefore, AQ, this to that. So AQ to AQ to AD sub 2. Or actually, we don't really need that. We can use it like this. It's equal to, so this to that is equal to this to that. So AE. So we know that this is true. Now we're going to utilize our thing here, this one. So how we're going to do that is we're going to write an equation not an equation, but we're going to rewrite AQ to Q D sub 2, because that's what we need to find, right? We need to find that AQ is equal to P D sub 2. So that's what we're going to do basically. And before we do that, let's start rewriting stops. Okay, so by convention, let AB equals C, BC equal A, and CA equals B. I don't think we really need to write this, but I'll just write it during the test because we don't know how the people, how they will grade it. So then we know that AQ to QD sub 2, so AQ QD sub 2 is equal to AQ to QD sub 2 is equal to as I mentioned, this to A E sub 1 to E sub 1 to G, as I mentioned, because these two circles are homothetic with respect to A. That means we can use similar triangle to just prove it. This is equal to A E sub 1 over E sub 1 to G. And let's see what is A E sub 1. And notice that This is also a really basic thing, but I never learned this though, but I think this is really rudimentary thing that we should all know. So we know that a e sub 1 is equal to s minus a. And that is because this plus that, so red plus green plus this black is equal to s. And we know that, oh, not blue, sorry. So we know that this, so whenever we have like something like this, a, b, b, c, c and a, we know that this length right here, a, is equal to a plus b plus c minus b plus c, right? And a plus b plus c is equal to s, and b plus c, and b plus c is equal to this length. So using that, we know that this is equal to s minus a. And what it is, e sub 1 g. So let's take a look at this whole thing. So e sub 1 g. So what is e sub 1 g? We know that cg is equal to, wait, let me just quickly write that. For clarity. Because we're going to use this a lot here. I don't like how I wrote it. Yes. So we know that e sub 1 g, this whole length right here, is equal to, so I'll just write it here. So e sub 1 g is equal to, let's trace some of our sides. E sub 1 c plus cg, and the reason why I did that is because we want to change it like this. Cg is equal to c d sub 2. And what is e sub 1c? E sub 1c is equal to, e sub 1c is equal to c d sub 2. What am I saying? Wait, it is indeed c, c d sub 1. And the reason why it's equal to c d sub 1 is because, like, just, we know this is w is, omega is our in circle, and e sub 1, d sub 1, they're where they meet, so obviously these two lengths are equal to each other. Just to prove it, we can draw like a right angle like this, and we prove that these two are congruent. But I think everyone knows that, so I'm going to skip it. What is c d sub, wait, it's c d sub 2. Now we know that c d sub 2 is equal to b d sub 1. That's given by our problem, by construction, plus c d sub, b d sub 1. And this one plus this one is obviously equal to a. So we know that this is true. Now let's because we know that because we know aq to q d sub 2, why don't we try ap to p d sub 2? That way we utilize the 3 points, p d sub 2. And like always, this is equal to, so what is ap? Yeah, how do we find ap? AP to p d sub 2. How do we find that? How do we find AP to p d sub 2? Wait, how do we p d sub 2? Let's try and find p d sub 2 first. AQ, this one is equal to, yeah, so it is right. Yeah, there's no other way, right? This to that or either this to that. What is AP? How do we find AP? Why don't we utilize that P is the intersection of... okay. Yes. I finally remember. Okay, so before doing that, let's bring it down here. I want to erase them. Let's use Menelaus, and we're going to use Menelaus for triangle ABC and B E sub 2. So we know that. Where should we it actually doesn't matter. We can go from here to here, and here. Or we can either go like this. Yeah. But because we want to find this to that, but if we use this one, so if you use BC, if we start from C and go to B, like this to that, this to that, then we will have BP over P E sub 2. However, we want AP P D sub 2, and what we can do here is just start from C and go to A instead of B. So here to here, and we can have AP to B PD sub 2. So we have, let's use Menelaus. C E sub 2 over E sub 2A is equal to AP, what am I doing? Times AP over PD sub 2 times D sub 2 B over BC equals 1. And that's what we wanted. AP over P D sub 2 is equal to C E sub 2 times D sub EB what? E sub 2A times BC. And what is E sub 2A? So what is this length? We obviously know that this is equal to C E sub 1. So C E sub 1 times BC. BC is just A, I will just write A. And what is C E sub 2? What is this? What is C sub 2? C sub 2 is equal to E sub 1, which is S minus A. So S minus A here. And we have D sub 2B. So this one right here is equal to C D sub 1. Am I right? Yes. So this is equal to C D sub 1. And let's continue writing. What is C E sub 1? What is C sub 1? C sub 1 is B minus S minus A times A all over. Is it right? C sub 1. Wait, C sub 1. It is indeed B minus A E sub 1, and that is S minus A. And what do we have here is S minus A times. What is C D sub 1? So what is this length? It is A minus S minus C. Wait. C sub 1. C d sub 1 is A minus. Wait, we should be able to cancel these two terms out, but not sure what went wrong. Let's look at B d sub 2 again. B d sub 2 is equal to. Wait, what did our problem? B d sub 1. Wait, so it is true. So B d sub 2 is actually equal to C d sub 1. That is correct. And we have this equals A minus. Sorry. It's A minus S minus B. This one. Okay. Then we know that this is A plus B minus S. It starts to A plus B minus S. So these two cancels out. And this is equal to S minus A over S minus A. Therefore, we know that AQ over DQ square, DQ sub 2 is equal to the reciprocal of this. So AP over PD squared. PD sub 2. So we know that this to that is equal to this to that is equal to this to that. This to that is equal to this to that. Let's just say that this is X, Y, Z. Then we have what is AQ? X over DQ is Y plus Z. Wait. QD sub 2. This one is equal to PD to Z over AP is X plus Y. So simplifying, we have X squared plus XY. We can cross multiply. We have X plus Z squared. So we have Y times Z minus X, X minus Z, X. So we have two cases from here. First one is when X is equal to Z. Then we have it true. So 0 equals 0. 0 equals 0. Then case is when X is not equal to Z. That way we have X plus Z equals negative Y. So X plus Z plus Y equals 0. But we know that this is impossible by construction. So we know that X equals Z, and therefore AQ equals P D sub 2. And we finished our proof. Wait, what? AQ D sub 2 P. Yes. So this problem actually taught me so many things. And first thing here is that, like, the first kick here was W sub 1 is tangent to BC at D sub 2. And the second one is knowing that it's homothetic. So these two circles are homothetic with respect to A. With respect to A. And third technique is noticing that AE could be written as S minus A. So that was something new to me, but I think most of us know it. Yes. And fourth one is, like, I don't know how, but we have to use Menelaus here. So I really love this problem. I learned so much from this problem, and I just found it so interesting, and it was just so amusing to read the solution, like the official solution, because of the beauty that it manifests through its elegance and like somewhat, I would say, like eloquent delivery. So thank you so much for watching this video, and in the next video, as I mentioned, I'm going to explain these two things. So please look forward to that, and thank you, and see you tomorrow. Bye.